All right. So today, in the second part of our SQL module, we're going to focus on constraints and relationships. Both of these are super fundamental. You guys have seen some of these already. The primary key that we saw yesterday, in fact, is an example of a constraint. And we've talked about relationships, but we'll go a bit more in depth with them. We'll also sort of do a tour of the most common constraints in Postgres. Postgres has a lot of constraints. Um, but the check constraint that checks that a value is something, a not null constraint, a unique constraint, which has a couple of interesting uses, are the big ones. And then primary and foreign keys are actually constraints. And then in part two of the lecture, we'll dive into relationships. We did some modeling yesterday, but we'll actually write code for different types of table relationships, one-to-one, one-to-many or many-to-one, and many-to-many. And we'll see an example of a join table to implement a many-many relationship. We might do a little diagramming along the way or use a spreadsheet, but it's going to be mostly a writing code day. And I'm actually just going to have our lesson open here because we're going to kind of be moving through these examples, and especially for folks who want to code along, that way you can have the code there. I don't recommend coding along, but I know people are doing it. And also I think when watching the video, it's useful to see sort of it reinforced twice. So I think that'll be good. Um, Big picture data consistency is the big deal with all of this stuff. Um, Postgres enforces all sorts of rules around relationships as well as with constraints. And so we're going to see how constraints and relationships really let us create a data structure that a relational database engine like Postgres can maintain and maintain that data integrity. Do folks have any questions before we dive on it? Okay, cool. And at some point, we'll circle back to our game store. So, um, we've kind of talked through already the main kinds of constraints. Constraints are rules. And can everyone read this okay? Okay, awesome. Constraints are rules that we define on a column, right? So in this case, in fact, for the game store, the action figure here is a constraint. Or I'm so sorry, the primary key here is a constraint. So our syntax is column name, column type, constraint. The Postgres docs lay this out really well as well, and I think their docs on constraints are good to look at. Um, but let's build a couple of these out. The most common is a primary key constraint. Let me make a file here for us to work with. And before I get too deep into this, I'm going to log into Postgres. I'm going to create a database named Avenger SQL2, and I'm going to connect to that database, which currently has no tables. So let's create a table of students and use this to talk a little bit about primary key, that we've already seen it. Normally we just name this column ID. So here I have an ID column, and I'm adding not only a constraint, but a type here. Serial is actually a type that we can add. It's a numeric type, as we kind of saw yesterday with some issues. And let's go ahead and add a student name. and limited to 255 characters. So primary key again is used to uniquely identify a row in a table. So if I had to use a spreadsheet to model our table right now, I could have as many students as I want with the same name. Excuse me. And it is this primary key ID column that we use to uniquely identify the table or uniquely identify a single row, a single student row in the table. So let's go ahead and run this SQL. Let me make sure I am in the right directory. And it looks like I created this thing in the wrong directory. So let me move the file out of the game store directory and into our main directory here. Because in Postgres, when I use the /i command, by default, I'm giving it a relative path. So that was the error that I ran into there. And that's, I think, a common gotcha with this. So now, in fact, I get the tabbed autocomplete. I run into another really common error, which is, I think, a huge gotcha with SQL, which is SQL does not like trailing commas. And now I've created a table. And we see, as we were discussing yesterday, this really interesting default value here for the student ID. Note that the primary key constraint does a couple of things. It sets it to not null, and we get that for free with the primary key constraint. And then it uses what's called a sequence, which is how Postgres handles like auto incrementing values, to generate the next ID value. I could go ahead and insert into students. And let's just go ahead and insert one. And here, I've made a mistake with my insert statement. If I'm saying values, I also need to, before that, put the column names like this. And this error relation students already exists is because Postgres sees this table already exists, and so it doesn't run this again to create it. However, if you guys look down here, see where it says insert 01. This is telling me Postgres looked at this code, ran into an error, but it continues executing SQL. So the errors don't actually stop our SQL file. Normally, Postgres will execute all of them, so even if it hits an error. So here, in fact, we see a successful insertion. I forget what this first value 0 is, but this one is telling me that I believe one row has been modified. And if we do select star from students, we've got Bob in there. So as we saw yesterday, I always want to use the pattern drop table if exists when I'm working on code. because it gets rid of that error. This way, if I modify the table, it's there, and it makes my workflow much easier. And I just want to pause and check in and see if folks have any questions. Cool. And I think a good amount of this should be review, but I figure this can also warm us up and we'll see a couple things along the way. I do want to point out another way of making primary keys with something called identity columns. Because yesterday, we ran into an issue where if I'm inserting some information, let's have it just be Carol and David. So here I'm actually inserting ID values, and let's insert an ID of 2 and an ID of 3. And that works. I'm curious if we can reproduce the error we saw where with the CSV file, like once we had added manual ID columns, it broke the sort of sequence of auto incrementing and auto generating IDs. So let's see what happens now. Now that we've manually entered some IDs and we switch back. So here we see this really interesting error. Duplicate key value violates unique constraint, student's primary key. Key ID 2 already exists. So this was what I was kind of struggling on yesterday, and this points out a little bit of the trickiness of if we're manually inserting IDs. And if we examine our table again, again, we see that that primary key constraint does a couple things. It adds an index so we can look up students really quickly, actually using a type of tree. It makes it not nullable. And then it's using this sequence where we see you can actually use functions in SQL. You can define functions, and Postgres has a tons of functions. And so in an SQL query, you can call different functions and stuff, so that's more advanced. And we see here there's this function call next val to not a table, but what's called a sequence, and then this sort of regular class element. So we're grabbing the next value in this sequence. And if we use the describe sequence command with pSQL, let's just try D for describe. Oh, actually, it needs to be students. There we go. We see that this sequence is an integer sequence. It has a starting value, it has a minimum value, it has a maximum value. It increments by 1. You could have a sequence sort of loop if you wanted. So these are all the default settings for a sequence. If we wanted to mess around with it, like days of week or something like that, or days of the year, you can get a lot more control over this. However, the challenge here is that we've kind of hijacked the sequence because we've manually inserted ID values, right? Now yesterday I ran into some trouble because I think the sequence didn't exist yet because we hadn't used this serial data type, and that sort of threw me for a loop. But now the sequence does exist. Note, by the way sequences are named, it's the table name, the column name, and then SEQ, short for sequence. So that's sort of a syntax that you can rely on. So now we can use the same approach that we did yesterday, which is we need to tell SQL, we need to tell Postgres to update the sequence. And actually, I'm going to pull up my guide code for this because this is easy to get wrong. So we're running a select statement, but we're actually calling this set value function. And inside it, we're running another select to tell set value what to update. And we're saying get the maximum value from this ID from our students table. And we're setting the value of the sequence to that maximum ID. And I forgot an S here. And let me go ahead and copy this and put this in our code. And one moment, Carlos. So if we put that in our code and then after that we insert Evelyn, if I run this SQL, we now see that that insert succeeds. Carlos, yes, sir.
So the select set val, and then you have the actual table name, right? The student ID sequence.
Mhm.
Um,
Sequence name, but yeah.
yeah, well, yeah, sorry, sequence name. So does it just by default, like I'm assuming there's only that one column? I'm a little confused as to how it knows what value to set, or is it just something you just got to take,
Right.
and that's what it
Great,
does.
great question. We actually have two SQL queries here. We have one select statement that we've kind of shoehorned this set val function into. And if we look at this function call, it takes two arguments. The first is the name of the sequence. The second we see is a subquery. So this second value is the value that we want to set the sequence to. But rather than putting in a number, like I could put in 3 and this should work. And if I do select star from students, Carol or Evelyn should have an ID of 4 because we set the sequence to 3. And then when we inserted Evelyn, it generated the next value.
I think.
However, obviously that's not very desirable to have to hard code this. And so we actually do a subquery that's a select statement. And we haven't talked about max, but there's a lot of, this is also a function essentially that's saying get the maximum value that's currently in this column from this table. And so we're grabbing the biggest ID value and setting the sequence to that.
Yeah. Well, I guess maybe my question was the you're only specifying the sequence, and I think maybe it's just like the structure of that sequence, the student's ID sequence is kind of maybe throwing me off, but I'll just probably do a little
Oh, you
research
mean
on
like the
that. Yeah, because I mean,
name?
yeah, I understand like how you're getting the value you want to set, but not where you're telling it, hey, in this sequence, just by default set val on a sequence, just set the next value, or how is the sequence table built? Because when you want to describe the sequence, um,
Yeah.
it showed a bunch of different fields.
Yeah. So yeah, a sequence is not really a table. And I think that's kind of the thing. And this is getting a little in the weeds, but this is good to mention because our database has a couple things. Indexes are also not tables. Let's actually see what Postgres says a sequence is. So I guess under the hood, Postgres might use a table, but that's the same way, like in Python, I can use a list inside a class. Like we're not meant to interact with this like a normal table. A sequence's job in Postgres is to be a sequence number generator. And that meaning a sequence starting at a certain point, it can generate different kind of numbers. The sequence has a minimum and maximum valid value, a certain amount that it increments by. And it could loop. Again, like think about days of the week, like 1, 2, 3, 4, 5, 6, 7. We might want to have a sequence where after 7, we go back to 1 to indicate the day of the week. Or the days of the year, right? 365 and then going back to 1. Um, so I think it's using a table under the hood, but again, it's not really meant to be used like a normal table. Let's see if the AI. Yeah, Postgres also has objects, which is not worth going into. This is really the main thing. We use a sequence to generate a unique ordered series of numbers. Um,
Yeah, I think that's my main issue right now because I think I'm still thinking of the sequence as a normal table, and I think once I get around that or get around to understanding that, I think it'll make a little
yeah,
more sense.
yeah, totally. Um, as I said, Postgres is kind of amazing. It actually has a sort of object structure under the hood in terms of how it's designed and built. So tables are a type of object in Postgres. Um, but we're not really meant to interact with them that way. But Postgres has other objects as well. As I'm not sure if they use a table to build a sequence. There's stuff called views, functions, and a bunch of other things. You can in fact write Postgres extensions and do all sorts of amazing stuff. So I don't want to get too in the weeds there, but just to like open the door a little bit on that. And you're correct, like this kind of like looks like a table, but it's not.
Thank you.
Absolutely. Great question, man. Um, and I just want to pause and see if folks have questions around sort of what we're doing here and the implementation steps. Okay, cool. I do want to show one more thing with primary keys, and then we'll move on. There's two ways to make a primary key. Um, Using this serial type that generates a sequence is one way. Another way is using something called an identity column. And this is actually a bit of a better way, but it's a bit newer, and all of our curriculum and stuff kind of uses serial, so I'll probably stick with that. But I did want to point this out. Um, Identity columns are actually sort of an SQL standard, so you'll see them across other databases, such as MySQL or Microsoft SQL, while Microsoft SQL and MySQL have some version of serial, the serial is actually a Postgres thing. Um, there are a couple other advantages to an identity column as well. It's a little more, I think, explicit about what it's doing. So if I was to make an ID this way, it would look like this. And this does the exact same thing. In fact, we still would have to do this because it's still creating a sequence. It just sort of hides the sequence away a bit more, but we would still have to do these same steps if we were manually inserting ID values. So this is just another way to create a primary key. It really, for the purposes of our course, won't make a huge difference. This is considered the better practice, but you'll see this all over the place. And as I said, our curriculum has this. So if you have to choose, honestly, I would just stick with serial right now. Andy, yes, sir.
The keyword here as, does that mean it's given it an alias or
That's a great question. let's actually see exactly how that works. I don't think it's an I don't think it's an alias, though it sure sounds like it. I agree with you, and you'll see as used that way in other cases. Um, I don't know enough to know, but I'm pretty sure identity, we're telling it that this column is an identity column. That as in like we're going to use this column to identify the row. As in, and there's different, I guess you could have an identity column that's not a primary key, but a lot of the times, that's what you would want as a primary key. Um, yeah, good question. Um, an identity column does not guarantee uniqueness. So identity is a little more flexible because maybe if we get more complex data modeling, we want something as to help identify that's not a primary key, but that's a little out of scope for right now. Yeah, great question. All right, let's take a look at the unique constraint, which I've been talking a bit about. And let's go ahead and let's build out just a user class and we'll add an email and use the unique constraint there. And this should look pretty straightforward. This should all look a lot like what we're used to seeing now. Oh, but I don't want the trailing comma because that will break stuff. And let's go ahead and run this code. And oh, it looks like I had a typo in this code that I ran. Um, I'm just going to comment this out for now. I'll fix the syntax error here later. I think I'm not combining primary key and generated by default together the right way. So I'll fix that one offline and make sure that the correct working one is in demos and notes. So now we can fix this, but I need drop table if exists. Users. And now if I go ahead and examine this table, let's see what we see here. Look under indexes here. And if you guys notice, we see an index has been created for the primary key, not null. But then we see another index has been created for the email column named users email key. And we see here unique constraint. And so a Postgres index is how we enforce uniqueness on a column. And let's very quickly look up what a Postgres index is. We're not going to be doing a ton with these, but it's good to see. So they're most commonly used to enhance database performance. And it's basically, you could think of it as a lookup table where it lets the database find and retrieve rows much faster than it could do normally. It does add extra work because when you add a new row to a table that has an index, the index also has to get updated. So think of like building a data structure if we were writing some code to insert something into an array or a list in Python, but we always checked to make sure that we didn't have a duplicate of the value in there already. If we wanted to construct a list of unique integers, that's very much what an index is doing here, where we will only insert new values into the index. And so that's how we can use an index to enforce a uniqueness constraint. Do folks have any questions about indexes or the unique constraint? And we can go ahead and insert a little bit of data here. And let me make sure I'm getting. Yep, I just wanted to make sure I had my strings right here. And let's watch our uniqueness constraint throw an error here on our email index. And it looks like I have a syntax error in this code itself, which I apologize for. If we scroll up a bit, insert into.
Do the uh row names need to be in quotes?
Oh, that's what I got. Yeah. Thank you so much. My
I did
brain
that
just did
yesterday.
not want to see it. Yeah, because that's what I was looking for specifically when I was scrolling before running this, and I still got it wrong. There we go. And so we see this first insert statement works fine. And then we get to the second one, and we see duplicate key value violates unique constraint user email key, detail email alice@gmail already exists. That insert fails, right? If we had a third insert with a different email, this one would succeed. And so again, we see SQL, an error will not stop execution of an SQL file, which I think can be a bit of a gotcha. And do folks have any questions around unique? Okay, cool. There is one thing I do want to show with unique that's good to see, which is using it for multiple columns. So in this example here, we could have a unique constraint for a group of columns. There's a couple scenarios where we might want to do this. Maybe we want to have a database of superhero names. But unlike normal person names, every superhero name has to be unique, right? Because you don't want two superheroes with the same name. That wouldn't be fun. So let's give our superheroes an ID. Let's give them a first name, a last name, and now we'll add a unique constraint here. So there's a comma here, I believe. And we'll give the names of the columns we want to be unique combinations. So now if we're inserting into our superhero names, and this is a terrible superhero name. Oh, thank you so much, Mike. There's no S at the end of last name here. I'm gonna set myself up for trouble. And let's put in two Wonder Womans. So we don't want two superheroes with the same name. That would not be fun, right? So down here, we see a whole bunch of successful insertions for all our other stuff. But all the way down here, we see p-SQL constraints, duplicate key value violates constraints, superhero names, first name, last name key. So this combination has to be unique.
Okay, so using unique like that means the first name can be the same, the last name can be the same. It's just the first and last name cannot be the same.
Exactly. Like if we wanted a superhero named Wondrous Woman, this should work just fine. And if we do select star from superhero names, indeed, we see Wondrous Woman made it in, but Wonder Woman did not. We're going to learn about join tables later for relationships, but for a table well, I'll show an example of this with relationships later on when we get there. Because I don't want to preempt that, but we'll see where this comes in useful. What we'll see is when we look at like students enrolling in courses, this is a useful way to make sure that a student doesn't get enrolled in the same course twice. Mike, yes, sir.
Do you know why it skips ID 4?
Interesting. I didn't notice that, but I can make a guess. It looks like with this insert statement, it must have updated the sequence that it uses to generate the ID, even though the insert failed, which just points to how under the hood Postgres is just code. Because you could imagine writing like Python code to do this and deciding to like do, ID plus equals 1 before you check the uniqueness constraint. Yeah, great catch. Great catch. Carlos, yes, sir.
I think if I remember correctly, I think Francisco might have mentioned yesterday that like even though we may not see it on the table, it still kind of stores that value as like it was used at one point. I don't know if I think I understood him correctly for that sequence table. Like we don't see it up in the front, but it kind of like somehow keeps in a memory, something like that, that it was used before.
Yes,
Mentioned something along this line.
yes, that makes sense. Exactly. I think I think that's the same thing in different words. And if we look at the super hero names ID sequence, I don't think it's going to tell us too much interesting stuff. Never done a select on a sequence. I'm not sure if it'll work. Uh, it does. Doesn't tell us a ton, apparently. But there's stuff there. And this is where this is stored. The sequence, and we see the last value is 5. So at this insert statement, while the insert of the data into the table failed, looks like it did increment the sequence. Cool. Any questions around this scenario for the unique constraint with 2 columns? This is a good one to be aware of. It can be super useful. Sometimes you might use it with the primary key, but sometimes, like we see here, we don't. This does give us what's called a composite primary key. Where if we enforce this unique rule, then we can say that these two things do uniquely identify a superhero. But in terms of like efficiency and data lookup, it's still quite nice to have an actual single primary key column. But in terms of database terminology, you might see the term composite primary key. And that's what this means, where you can use multiple columns to uniquely identify a row. Any questions before we keep rolling with constraints? Okay, cool. We are almost done here. We're going to look at the not null constraint. And then we'll do a little application on the game table, and then we will take a break. So the not null constraint is pretty straightforward. It's what it sounds like. You add it to a column so that the column is not null. And let's look it up real quick to see if there's anything interesting. By the way, this site, Neon Postgres, has very good tutorials, and it can be a bit lighter weight than the Postgres docs, though I do think the Postgres docs are quite good. This makes an excellent point right here. Null has a special meaning, really like it should, ideally in programming. It's not an empty string. It's not the number 0. It means an unknown or missing information. Right? So when, at least at the data layer of our application, we should always use null this way. Null is null. It's not 0. It's not an empty string. It means we don't have this data for this column. So as you design your data, you'll encounter situations where you have to make choices, but if you kind of follow that rule of how to use null, it'll help guide you in those scenarios. So it's pretty easy to use. I do want to go to the Postgres docs real quick. As always, they love throwing extra stuff in here. If we really wanted to, we could make a column be null or allow that the default behavior is null, but we're probably not going to do this. But if you wanted to, you could, for what it's worth. So let's build out this products table quickly. And I have a whole lot of insertions here. I think that's okay. There's not a ton to say about the not null constraint, as it's relatively straightforward. Where again, we're going to have an ID. We're going to have a product's name. And a product quantity. And in fact, let's make the product name not null as well, because I don't want a database of products where something doesn't have a name. That wouldn't make any sense or be any value, right? So not null, use this liberally. And again, think about data integrity. Like if I have a row of product information and the product doesn't have a name, that's not good data integrity. That's not what we want. We want our database to always keep the data organized and the way it should be.
Got some typos we'll need to fix.
Oh, where are my typos?
I think line 54 needs a semicolon at the end of it.
Oh yeah, thank you.
And then your quantity, it auto-completed to N2 instead of int.
Oh, thank you so much. Good catch. So let's insert some values into our products, right? Very exciting items. A wrench, a hammer. There will be 0 hammers. We will insert, note that not null lets you insert an empty string. But if I don't have a name value here, this will fail because name is null. And this will fail because quantity is null. And this one succeeds, even though it's not very good. So we'll see more constraints, how we can add some check constraints in just a little bit. But let's go ahead and run this code. So there's a lot of insert statements at this point because we have everything happening here. But if we look over here, we see this is the bit we care about. Products table does not exist. It's created. The first two insertions succeed, insert 0, 1. We have a row inserted here, a row inserted here. Then we see p-SQL constraints error no value in column name, right? So this is that failure. Then we see null value in column quantity, violates not null constraint. And then we see this last insert succeeding. So let's go ahead and look at our data. And again, we see that the not null constraint still allows, this is, not good data integrity. I don't want an empty string. I don't want a quantity of 0. I think after the break, we'll add check constraints and see how to tackle that. But not null gives us some degree of certainty, right? Let's see. I think there was one other thing I wanted to mention here. No, I think we've pretty much covered it. There's not a ton more, but not null. Let's take a quick look at the table schema. So we can see here this nullable, not null for these two. When we come back after the break, what we'll do is we'll add in some default values, which can help, right? This scenario, well, we'll add in some check constraints first, because default values will maybe help us avoid not null. So we'll see check constraints where I can say, hey, I can't have an empty string for the name, and the quantity has to be at least greater than 0. It has to be 1. And then we'll see default values. And then we'll update our game store, and then we'll start looking at relationships. Sound good? All right, why don't we take let's take like 13 minutes. So let's come back at 10 after the hour. Get up, get away from the screen. I know I've been doing a lot of talking. Hopefully it's good walking through this though. And then when we come back, we'll check out check constraints and default values and relationships. Thank you very much, and I'll see you all in a little bit at 10 after. All right. So just before the break, we had made a products table, and we were playing around with the not null constraint. And it's useful, but it causes problems. And if we look here at line 65, and in fact, let's have us have -5 of nothing. And if I run that SQL and do select star from products, we see that in our products database, we have -5 of a product with an empty string for a name, which is obviously not what we want in terms of data integrity. So that brings us to our friend, the check constraint, which I actually had skipped over. I think we were supposed to cover it sooner, but this is actually really good timing. As it implies, and as you can kind of see here, the check constraint is basically like an if statement where I can say, like, if age is greater than or equal to 5 and age is less than or equal to 10, return true. This is a valid value. You can use the check constraint for all sorts of stuff. So for instance, for here, we're going to check quantity is greater than equal to 0. Because having nothing in stock is fine, just -5 of something is not okay. And so now we see failing row contains 5, -5. It's a little hard to read this, but I'm pretty sure that that insert statement failed. And if we do select, we see there's only the wrench and the hammer. And we see this constraint violates check constraint products quantity check. So that's good. I can in fact even give my check constraint a name if I want to make this a better error message. And let's call this non-negative quantity. You don't have to give your constraint a name. And I think that worked. Let's see.
Looks like your guide code on the right is a little bit different than that. Or not guide code, but
Oh, you're absolutely right. We have to change the keyword from check to constraint. So let's put both examples up here. So if I want it all as a one-liner without a name, I just use the check verb. But if I'm giving it a name, I need to use the constraint verb. And let's comment that one out. And now
And
let's
then
give this a shot.
you still have
after-
to add check.
Oh, you're so right. Thank you. Yep. And in fact, I believe we can even do this. If we wanted to. And this, I think, actually probably makes more sense. And in fact, if we scroll down a bit. Nope, just to make life, let's see if this one works. I think that did work. Yep. So if I want to give my constraint a name, thank you guys, I have to say constraint name, and then the check and the rule of what I want the constraint to do. I can put it all in one line like this if I want. Or I can put it on 2 lines if I find that easier to read. It's really dealer's choice. And the only difference here is now it says violates check constraint non-negative quantity. So this is really more for providing helpful error messages to the developer and to yourself as the developer. Andy, yes, sir.
Is this is this the best practice to get that done in the back end, specifically in the database, because you can still fix that during front end and Flask stuff?
Right. That's a great question. Like, when do I want my validation logic? Let me make this a bit thicker. So the way to think about a program is it's got layers, and sort of like an onion. Right. And again, the question basically is, hey, where do I want this validation logic? Do I want this validation logic here? Do I want it in my Python code that's calling it? Or do I even want it in my front end logic? You're almost always going to have validation in multiple places. And if you all remember from Flask, you had models, and then you had the views or the view functions that called them. And if you think about the way that data works, or with Flask, the way that an HTTP request kind of comes in. Let's make this sort of purple. Right, and we can say like data flow of execution, where maybe I get HTTP get Pokemon Pikachu is my get request. And then the response ends up being some JSON about Pikachu that's come from our database, but that code has flowed through the different layers and then the response back out. And even if we're not writing a web server, we still see this same sort of flow of execution and data flow for a program. And it's the same thing if we're inserting information. And I just want to check in to see if this diagram kind of makes sense to people in terms of how to think about a program. Awesome. So the rule of thumb is the deeper you go, the harder it is to change stuff. Because if I change this Python code here, I might have, and I'll just use black. Like I might have a function here, and maybe it's like, I don't know, def, get Pokemon. And I might have, and let's move this here. And I might have another function here, and this one might be like def create Pokemon. But then in my models, this Pokemon model is used by both of those functions, right? If you guys remember Flask, is this ringing bells? And then in here, and we could even have like different Pokemon models or whatever. But then in here, we've got a Pokemon table. That could be used by the Pokemon model. It might be used by other models. It's used by all sorts of stuff. So the deeper you go in the code, the more like this table is used, probably is called by a number of different functions and things. So changing this impacts a lot of different stuff, right? Changing this impacts a middle amount of stuff. Changing these outer layers of the code is the most self-contained change because it only impacts itself. Do you guys see what I'm saying? So there's a trade-off. The deeper you go in the onion, the harder it can be to change stuff because it impacts more things, but the more power the change has. So in general, so Andy, to go back to your question of do I want my validation logic here? The answer is yes. I want my most important validation to happen at the deepest level so that everything can take advantage of it, especially things that are sort of fundamental rules of the universe that I'm creating. Like in my universe of inventory, a product with an inventory of -5 simply cannot exist. And that's a real early design decision, right? That I'm making as a programmer. So I'm going to put that in the data model. I might duplicate that logic here because it reduces calls to the database. Like, because if I'm doing something that I know is going to break a database rule, like I can make this code respond quicker and not have to like call the DB and have the SQL fail and stuff. But that's more of a design decision. Um, Other logic, like maybe for a certain kind of product, we always want to make sure we have at least like 10 tins of cat food in stock. That's a great example of something that belongs out here, right? Because it's more specific, it's subject to change. Tomorrow it might be 20 tins of cat food that we want in stock. The next day it might be 0. Code that we know is going to change more belongs further outside the onion. Does that help answer your question?
Yes, thank you.
Yeah, great question. Great question. And I think this is a really good model to start thinking about your code. This is also, by the way, why like unit tests for models can be useful because your unit test sort of has a bigger surface area. While like unit tests for this stuff are a bit less useful, but like an end-to-end test is more useful because an end-to-end test tests this whole flow of execution, right? And so kind of building in your brain that mental model of like when I'm executing code, like what's the flow of execution when it's hitting, the term is test coverage. When I write a test, how much of my code does it cover? If you guys kind of start building those visualizations and mental models, it'll help a lot. So that was a little bit of a segue, but a good one. Do folks have any questions on this? And again, great question. Before we keep rolling with constraints. Cool. The other thing to think about with SQL and constraints is once I have real data in here, it gets harder to change the database, right? If we are Walmart and we're building our product inventory database, and I have, millions of rows of data for product inventory, all of a sudden changing a check constraint could have a whole bigger impact. And so for a company like Walmart, in fact, like changing the data model is a much bigger deal. So there are things of scale to think about too. And once you have real data, it gets trickier. For us right now, the good news is when we're developing, everything is small and we can change it. All right, so let's keep rolling with constraints. We've seen this non-negative quantity constraint in action, which is awesome. Let's see how we can also add a constraint for the name so that an empty string is not okay. And the way we're going to do this is we're actually going to use Postgres functions. Postgres has a ton of functions. The comparison operator is actually a function. Their tables here are not the friendliest, but and should look familiar. Between or not between. Distinct is not distinct. Is null is not null. But we're going to use string functions. And down here in string functions, somewhere around here is length. There it is. So Postgres has a function called length, which will return the number of characters in a string. And this is a great starting point. And we're just going to say here, check length, and you can make it lowercase if you want. I think the convention is still sort of uppercase. Length name, let's say, is greater than 2. So name has to be at least 3 characters long. And so let's make this cat. And now this fails because quantity is negative. And now let's make this high, and we'll just make it a quantity 5. Fails because name is too short. So now if I look down here at my constraints, we see all the way down here, failing row, error, new row for relation, violates check constraint, product names check, which is sort of the check that it's generated. And if I do, excuse me, let me get my cursor back. We see again, we only have a wrench and a hammer. But if I insert 5 cats, this should work just fine. And indeed, we see our cat. You can also use regex, and I'll show that in a moment with our game store. But I wanted to show this use of a Postgres function because this is super useful, right? There's a function, by the way, to convert the first letter of a word to capital for printing stuff out. This format string function is incredibly useful. I would definitely be Googling and asking GPT, converting something to uppercase if you need to do a comparison, or converting something to lowercase if you need to do a comparison, getting a substring. So again, the Postgres functions are pretty awesome, as are all the Postgres functions, and you can find them here. Like and similar to are sort of the biggest ones that we'll see later. But it's super useful. So let's hop back to our game store. And let's look at this with fresh eyes and use all of these constraints that we've learned. So for my action figures, we know this is going to be a primary key. I know the action figure title is a varchar, but it might be useful to make sure that, say, the action figure title is alphanumeric and doesn't include like exclamation points or other symbols or stuff like that. And we can do that with a regex and a check constraint. So I'm going to be a little lazy. I'm going to say is not null. Check. And then we'll check action figure title. And here we'll add some regex. And we'll use this curly Q symbol that indicates the Postgres. We're going to put some regex here in single quotes. And hopefully my regex is correct here, that this is going to be alphanumeric. I'm not a regex wizard. Far from it. I'm definitely going off of some guide code here. And I believe what this is saying is each character needs to be in one of these groups. Does that sound right? If anyone's more sort of regex savvy?
So you're saying the upper arrow, beginning of the string, then you got a grouping. It can be capital letters, lowercase letters, digits. Then plus means one or more, and then the string ends. Do you not want spaces in there? Maybe?
Oh, a space is a good idea. So would I want to put a space like that?
Yes. But the problem with that, with one is this simple. I think it could be all spaces technically. but I guess
Oh, yep,
it depends on what the
yep.
titles are going to be.
Update this Postgres regex to allow for spaces between words. And it would help if I pasted it in up. But what it has is really simple. And this gets already more complicated because we're grouping things. And so it looks like we're allowing for
Yep.
groups. Yep, it got rid of the 0 to 9, which is fine. I think I'll leave it.
Yeah, it
So
looks like it's going to start with a word, one or more letters in the A to Z, and then there's optional space and then another word and as many of those as you want.
yeah. Regex to enforce only uh, letters, optional space between words. Yep. And Nick, thank you for the breakdown. This is very much how I use regex. To be honest, this one's relatively straightforward, but if I was doing this for real, I would probably anything that's like non super obvious for a non-regex person, I like to put in comments because I'm not very good at regex, and this way, if someone else reads my code, they can maybe get a hint of this. If this was a Stack Overflow post, I would actually link to the Stack Overflow post. These days, Stack Overflow is kind of dying, but we can see here kind of the value of a regex, but also the pain and why like not null and these other things are useful. And quantity again, here, let's add a check. So for our action figure, the quantity should be greater than equal to 0. And as you go through here, we could see the same things where our employee name, let's say we want to have letters only, must start with uppercase letter. And I'm actually going to use ChatGPT to help me here. Truth be told, I actually do not recommend putting string data as case sensitive unless you actually need it, because then your string comparisons become super painful. In your data, I recommend lowercasing as much as humanly possible. Again, unless there's a need. And then when you pull your data from your database to go back to the onion, like, over here, this is where you can have, capitalize first letter or whatever to format your strings. Now, if I'm putting like entire sentences and paragraphs in there, that's obviously a different story. But for names, lowercase everything, unless like specifically we might ask you otherwise just to kind of test you on regex. But as a general design rule, it makes your life easier and string comparison easier. Um, and this again indicates some of the trickiness of data validation this deep in the onion. With this regex, I'm getting rid of the possibility of middle names, right? A middle name here would be invalid, and I'm deciding for all time my users have to have first name, last name. Um, and this is actually a pretty good example of where I might want to be really conservative and I don't want to enforce too much. I might just want to enforce alphanumeric, to be honest, for an employee name and not even worry about uppercasing or anything like that. So I think what I'm going to do is take this and modify it, and we'll say check employee name. I have an extra tilde there, so let's get rid of this. And let's see, I'm not sure how to, I guess it has to start with an uppercase letter, which I'll leave. And I don't think I'm going to build the rest of this out unless people want to see, but you could imagine for position, we might do something similar. For salary, we might do a similar check as well, that a salary has to be a positive value, for example. And so on for each of these fields, where there can be differences, and it does pay to be a little thoughtful. We're going to ask you to be stricter on the assessment, but in general, for design, you want to be a bit more conservative in your constraints and your data validation rules. This deep into the onion, right? At the center of the onion, be a bit more conservative. You can add validation for like capitalization of first letter of first name up here at this outer layer. Cool. I think that pretty much covers constraints. We should talk about foreign keys. This will lead us into the next part of the talk on relationships. So before we dive in, I just want to pause and see if folks have any questions around constraints and the check constraint and everything we've been covering. Okay, cool. Should we take 5? Or you want to keep rolling?
Keep rolling.
All right, let's do it. Let me go ahead and make a new file here. And let's start building this out. So a foreign key creates a relationship between tables, right? And we talked about relationships yesterday, and we talked about foreign keys. So just to build this out and talk through it as I do, if we have some employees, actually, let's make the department first. And employees work in different departments, and a department is going to have an ID, and a department is going to have a name. And our department name is going to have to be not null, and we're just going to do a check to say a really simple check. Length of department name is greater than 3. And that's really it for my department. And let me go ahead and run this code just to make sure I don't have any typos. And I think I put this code in the wrong spot. Now the code should be in the right spot. Let's try this again. And I do have a constraint or an error. And I need to save my file.
Your
I've
editing
changed
file
it.
was deleted.
Oh yeah, thank you. Don't save. Let's open up the file that I moved. And let's try this again. There we go. So my table's working. I have departments. Let's just insert a department. Right. The most exciting and the least exciting. And let's make an employees table. And our employee will also have a name. And an ID. And I think I am going to steal this regex that we had before for our employee name. So let's also, yeah, we'll just leave it like that. We could add a length check if we want, which I think would look like this.
Does it need to be just name?
It does. Thank you so much. And now let's add the foreign key, which is the department that our employee belongs to. And I can add this as a column. And then just the same way we can add a constraint, we can add a foreign key, which is a special kind of constraint. And now we have to tell Postgres what column and what other table to reference. Right. And so now if I can't seem to change the color of my code. Carlos, yes, sir.
Since just like a primary key, it's by default not null. Is it the same for a foreign key,
Correct.
or do we have to specify? Okay,
Yeah, great question.
thank you.
So this just forces department ID to be a value from the department ID. Like you can't pick anything that's not already in that table,
Yeah,
right?
exactly. Exactly. And let's go ahead. Let me make sure I don't have any typos in this code. And let me also draw my arrow to the correct ID column. Goes up here to ID. And let's go ahead and run this. And I just forgot my create table statement. And we'll just do drop table if exists employees there. And we'll just get rid of this arrow. And
Oh, you're trying to add IT and it's too short to departments. So that's one thing.
yup. Also character varying length name. Oh, I had this totally wrong. I need to make the function call for length only accept the name argument. So I need to take this column, this string column, this text column name and turn it into a number, into an integer length. And then you're absolutely correct. So we're going to make this greater than, oh, that's employee name. So that should be fine.
Yeah,
IT is department name.
yeah, you either need to make IT bigger or reduce the constraint on department name. Because right now it has to be four or
Oh,
more characters. IT is only two characters.
yeah, indeed. So great example of why it's good to be conservative in your validation logic down at the data layer. And now this should run. Relation departments already exists. Use drop cascade. Yep, we're going to talk about cascade in a little bit. New row for relations violates check constraint. Department name check. I think, right, because we're not able to drop.
Uh, so okay, so the drop is that cascading thing you have to do because it relies on other
Yep,
tables, and then our regex is
yep.
requiring the department name to start with a capital and then immediately become a lowercase. And the problem is IT is two capitals followed after each other, so that's that error, I think.
The
So
regex, I think, is only for the employee name.
name check.
Yeah. Yeah, the name check.
I know you're
Yeah.
right.
Yeah, but you're absolutely right about the other issue, and we're going to talk about cascade in just a sec. Um, let me go ahead, and if we do select star from departments, we see we've got accounting and IT. If we look at the departments table, we see a couple interesting things here. We see check constraints, but we now see over here this new bit referenced by table employees constraint blah 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 blah. But the constraint name is employees department ID foreign key. Foreign key references department. And so just like you guys were saying, we're about to see that I can add an employee. And let's do name, department ID. And I also now have to look at the IDs. Accounting is ID 1, IT is ID 2. And Alice is going to be in accounting. And I'll give Alice a capital A so I don't run into validation issues. Bob will be in IT. Carol will be in a department that doesn't exist. And let's run this and watch what happens. So down here, we see this error message, insert or update on table employees violates foreign key constraint, employees department ID. And we see the error message, key department ID equals 3 is not present in table departments. Right? So if I look at my employees, I've got Alice. I'm actually not sure why we don't have.
Bob's too short of a name. You need to have length of name be greater than
Oh,
2.
yeah, I meant this to be greater than or equal to 3, and I totally screwed that up. Or greater than 2. Yep. Again, showing just how tricky this stuff is. And I would recommend, by the way, when you're designing your SQL, don't add constraints like this in right away. You can already see how much pain this is causing me. Get your core columns and relationships set up. Things like not null, things like, for like inventory quantity has to be greater than 0, stuff that's really fundamental for your data model. I think it's okay to pepper that in early, but this stuff that's less critical, like about names and stuff like that, I would recommend waiting till you get more of it working. So now if we run this again, we see Alice and Bob, but no Carol, right? And we see this foreign key constraint. And if we look also at our employees table, we see the employees table also has this foreign key constraint, right? So this relationship, we don't have a relationship here, but if we added you know, employee. And let's just give them a department ID. And now we add a department. And I'm going to keep it simple just in the interest of time. So this relationship here, it's not just theoretical, right? Postgres enforces this. I can't have an employee that doesn't belong to an existing department. Alex, yes, sir.
So can two tables have a foreign key pointing to each other, or is that not possible?
You probably could. You wouldn't want to. You mean like if I had, I don't know, employee ID or something like this?
Yeah, I'm just saying like because does foreign key needs the other table to exist before it can kind of work, right?
Correct. If I defined the employee table first and I defined the departments table second, I will in fact have a problem. Um, at least I think I'll have a problem.
So that would lead me to believe that you can't just have foreign keys pointing at each other because one would need to exist before the other kind of thing.
Yeah. It actually looks like I was wrong here. SQL is smart enough. It reads this stuff in. Um, and it creates the department. And if we look at employees, um, actually it did not. I lied. It created department, but it totally failed to create employees because this foreign key doesn't exist yet. And if we look at this code we run, notice table employees does not exist, skipping relationships, error, relation departments does not exist. Right? And that's almost definitely coming from this foreign key statement. So as you write your SQL, it does matter the order that you create your tables based on your relationships. For that reason, you also do want to avoid circular relationships like you're talking about. Like if I add an employee ID column here, and let's give our employee an ID, and let's make this primary key just for our own clarity so we can see it's already the primary key, right? And then we grab this and we have this connect here. We also run into the issue, is this a one-to-one relationship? Is this a one-to-many relationship? But this sort of like circular dependency is going to cause problems. You would almost never want to do it. So I think you'd have to kind of go out of your way to make it arise. Does that help answer your question a bit?
Yeah.
Cool. Awesome. Let's talk about cascades. And then I think we'll take a short break. So let me go ahead and move my employee stuff back to where it was. And if I run my code, everything runs hunky-dory except for Carol, where department 3 doesn't exist. So let's comment this out for the moment, actually. So everything runs hunky-dory, but notice how I added up here on line 2 early on, drop table if exists employees. even though over here we're creating departments. And watch what happens if I uncomment this and run my code. We see an error. Cannot drop table departments because other objects depend on it. Constraint employees department key ID foreign key on table employees depends on table departments. Use drop cascade to drop the dependent objects too. So the issue here is, first, I have some pre-existing data because, when I run this relationships command, like these things already exist in my database, which is very often the case, right? If we were creating this database for the very first time, we wouldn't run into this issue. But it's so common that I want to modify a table or I want to drop it to rebuild it. And I'm running into an issue here. And Postgres is telling me, hey, I'm not going to let you modify departments because this other table that already exists, employees, it has a foreign key relationship to it. It depends on it. So if you want me to do that, you have to be explicit. And this is going to lead into part 2 of our lecture where we talk about relationships and cascade. And Nick, I believe you were mentioning this earlier. So cascade means don't only drop the table that we specify, but drop everything that depends on it. Foreign keys, indexes, so on. So you have to be really careful in using cascade, but you can see why it's important because sometimes if I want to modify data, but Postgres enforces all these rules, it's not going to let me modify our data schema, the shape of the database itself. So if I say cascade, like that, this now says to Postgres, hey, delete departments. And Postgres says, hey, I can't. This other table, employees, depends on it with the foreign key relationship. If I delete departments, then this department ID column data becomes meaningless and invalid, and I'll have IDs for departments that don't exist because the whole departments table will be gone and I'll lose data integrity. But then we tell Postgres, that's okay, cascade the delete employees too. And we see this notice, drop cascades to constraint employees department foreign key. I guess it doesn't delete the whole table. It deletes all the foreign key values, which is less useful in my opinion. And actually, I apologize. There was a great question about do foreign keys enforce a not null constraint? And I actually got that wrong. They don't. If we look at this data schema, we see that primary key has enforced an ID value, or enforced the not null value on ID, but the foreign key constraint does not enforce not null. So in fact, I would have to add here department ID not null as an additional constraint. And I believe this will actually now throw another error when we try to drop stuff. Let's see. Let's try it again. It looks like it's okay because I guess because we don't end up inserting empty values in here. But just to show the not null constraint in action, if we try to add someone without a department ID.
Let's see if it's.
To remove that comment at a close and
Oh, thank you. if you try to remove someone without a not null ID, and we do select star from employees. Oh, and we're not seeing the employees table dropped. I apologize because I was fiddling around with this. So there we go. We see our null value in column department ID of employees violates not null constraint. But if we didn't have this, right, that would work just fine. So foreign keys do not enforce not null by default. So that is an important thing to add. Because sometimes it's okay to have a null foreign key. Sometimes it's not. Maybe a new employee hasn't joined a department yet. Do folks have any questions around Cascade or foreign keys?
Just to confirm, so that the using Cascade doesn't drop the dependent table. It just drops any links to that dependent table.
Yeah, that's correct. And it deletes values. Like I'm getting rid of this drop table for employees. Let's run this again with the Cascade and let's see what department ID is for this stuff. And now if I do select star from employees, I guess it doesn't delete the values. I apologize. I thought, but it deletes the foreign key relationship. Because if we look at these two tables, that foreign key relationship is now I believe it's gone. Yeah, because we didn't drop employees, so we didn't recreate the foreign key. It's getting a little tricky now with all the modifications that are happening to keep track of stuff. But in fact, I think the easiest way would be let's do this manually. Let's run this. I've got my departments with the foreign key. I've got my employees with the foreign key. If I do select star from employees, we see they're there. Let's do drop table if exists departments cascade. And let's fix my typo. And let's fix my other typo. I apologize. There we go. Department table is dropped. It cascades to constraint foreign employees. If you look at the employees table, the foreign key is gone. If I select star from employees, so the data is still there. So we still have the department IDs, but the foreign key relationship is gone and Postgres doesn't know that relationship exists and doesn't enforce any rules around it. Yeah, great question. All right, why don't we let's take 5, and then when we come back, we will explore the different kinds of relationships. Specifically, we'll really spend a little time with many to one and many to many. Sound good? All right, thank you very much, everyone. I'll see you all in 5 minutes. All right, we've spent a lot of time on constraints. We've seen some really cool stuff. And then with relationships, we did a pretty deep dive into the foreign key constraint. We already talked yesterday about one-to-one versus one-to-many and many-to-one, and a little bit about many-to-many relationships. We'll see these more today. In the curriculum, there are a number of examples. And we've already talked about what relationships are, so I think we've covered this fairly well. And relationships are like the defining feature one of the key defining features of relational databases like Postgres or MySQL or Microsoft SQL, right? The tables, but also the relationships. So there's a number of examples here of different kinds for one-to-one relationships, and there's example code with employees and social security numbers, with passports and people, though it has been pointed out to me that a person can hold more than one passport. So this is a bit of a contrived example. Cars and VIN numbers, and many to many, many to one relationships. And it is, in fact, and for many to one relationships, we have students attending a university, customers that belong to different countries where a business wants to keep track of it, employees and departments like we saw before, and then many to many relationships, which can be the trickiest, where a student can be enrolled in multiple courses, or an actor can star in multiple films, or a book can have many authors, and an author can write many books. But the example that we're going to build out is sort of a student management database, because we get to see all of these in one. And students, we've got students and we've got lockers and we've got classes. And if we get to it, we'll have time for professors and grades. And a student has one locker. A student enrolls in one or more courses. Let's call it a course instead of a class. A course has one or more students enrolled in it. And I'm sort of practicing the database design process we looked at yesterday, where I'm starting at a real high conceptual level with entities and plain English sentences describing entities and their relationships. A professor teaches one or more courses. A course is taught by one professor. I'm going to make that decision that we don't want joint professors. And a student gets one grade for a specific course. And that one might be a bit trickier as we get there. And a course has many grades, one for each of its students. All right, if we wanted to calculate a class GPA, getting the grade of everyone in the course might matter. Or if we wanted to grade on a curve or something. So we're going to start out really simple. I don't know if we're going to have time to get to professors and courses, but we'll start with students. Maybe we'll go to professors because that's a one-to-many, and then we'll look at courses. And so let me build some of this out and diagram it out. I know that I'm going to have a student. I know that my student is going to have an ID and a name, and I'm just going to keep everything really simple for now because I want to focus on relationships. I'm not going to worry about constraints or checks or anything like that. That can come later. And a student has a locker. A locker has an ID. A locker has a number. A locker has a combination code. And a locker belongs to a student. So I think what I'm going to do is I'm going to add a student ID here. So we would have to decide which column this lives on, right? And this is going to be a foreign key that relates and it's a one-to-one relationship. And if I kind of go over here real quick, and we have student and we have locker. And we have combination. I can have student Bob has locker 1. What I want to avoid is where locker 1 is also held by Carol. This is bad, right? Because this is a one-to-one relationship. What's also bad is where Bob has 2 lockers. Right? Both of these are bad situations because I want student and locker to be a one-to-one relationship where this needs to be a unique combination of locker ID to student ID. So to build this out, we need to do a couple of things. And let me go ahead and start making tables. And I kind of cleared some space here. We're going to make our student table. And the ID is going to be a serial primary key. And the name is going to be a bar chart. But now for our locker, this is where it gets interesting. I'm going to grab the ID. The locker has a combination, and I'm just going to make this an int, not null, and now student ID. And we know this needs to be a foreign key, right? And my apologies, I'm actually pulling up some reference code here. So student ID is now a foreign key. So our locker can belong to a student, but I could still have like many lockers belonging to the same student. I need to create the one-to-one relationship, and I'm going to use a unique constraint to do that. And now I'm enforcing that I can't have a student with the same locker, right? Or I'm sorry, a student with multiple lockers. So I think we may need to add a little bit more here to get the unique constraint working, to get a one-to-one relationship working. Because I'm not sure if this will actually handle like both sides of the coin, where we don't want 2 students having the same locker, but I also don't want a student having multiple lockers. Because if we insert into, let's go ahead and make some students real quick. And let's make some lockers. And I'm going to remove this not null constraint just in the interests of time. I think we're going to see that we need to add a little more work to enforce the one-to-one relationship. And let's see here. I have a syntax error.
But you need to give it a combination for locker. Am I missing?
Yeah, it doesn't like the comma. I think
Because student ID doesn't have a type.
oh, thank you so much. That would totally be the issue here. So all of this inserted, and if I do select star from locker, I see that I have like one student with multiple lockers because each of these is still a unique combination. Right? 2-1 is different from 3-1. So I can't just have this unique combination rule. I also need to enforce uniqueness here on the student ID. And now if we run this, we see these keys already fail. And in fact, I have this here. And in fact, I might just need unique on the student ID. I might have made this overcomplicated. We can add in another student there. I'm not sure if Locker will let us. We could try modifying an ID. I think primary key enforces uniqueness. But I'm actually not certain. Let's see if this works. So it does enforce uniqueness on the primary key. And we see we only have these two here. So I apologize. I think this was a bit overkill. In fact, I don't think we need this combination here to enforce uniqueness because the primary key has to be unique and then the student ID has to be unique. And so I think that alone takes care of what we need to do. And oh, it looks like I apologize. I have a syntax error. I have a trailing comma from eliminating that line. And we see all these errors. And now if we do select star from locker, we see that the uniqueness is enforced. So I apologize. This is actually much simpler than we thought. So the one-to-one relationship is fairly straightforward. Let's look at a one-to-many relationship with courses and and I'm just going to comment out the students in the lockers. Let's look at one-to-many with courses and professors. Where I have a course and I have a professor. And we decided that a course is taught by one and only one professor. And let's just give our professor a name. They don't need much else. We could give them a department and stuff like that, but we can worry about that later. And now we build this foreign key relationship between course and professor that is one-to-many. And this is very similar to what we saw with employees and departments.
Do you want the relationship to be backwards now? Right now, it looks like one course didn't have many professors.
Oh, thank you so much. Yeah, I diagrammed this wrong. We want to go the other way around. And in fact, let's create the professor first. Since the course has a foreign key, if I create the course table first, I'll run into an error because it'll try to reference a professor that doesn't exist. So let's make our professors. And let's grab that ID. Let's make a name that's just a varchar. And that should really be all we need at the moment for a professor. And we'll create a couple of professors with names. We're going to have fancy professors. Like Einstein and Newton and Turing, because why not? And let me run my code real quick to make sure that everything's working. And everything looks good. So now let's make our course table. And the order does matter because again, we have the foreign key here. And if we had made the course table first, it would throw an error. And let's give the course a name. Courses are definitely ripe for categorization, but I'm not going to worry about that in the interests of time. And we're going to give a course a professor ID, and this is going to be an int. And then we're going to add a foreign key, and I'm actually going to grab my reference code and just paste it in here. Make sure I get it right. So professor ID, and let's say that a course has to have a professor. References our professor. And now we can create some courses. And we'll have like Physics 101, which will be taught by Einstein. You know what? Newton will also do a Physics 101 because maybe a course isn't just a list of the possible courses, since it has students and professors. Maybe it's a really big university. And then Computer Science 101 will be taught by Turing. And so this is also, as you can see, a benefit of being a bit more liberal with my constraints is in the real world, there's a lot of scenarios where a course might have the same name depending on what we're modeling with our data. And if I select star from course, we see that we've got courses with professors. If I examine the course table, we see that foreign key constraint. So I just want to pause here and check in and see if folks have questions around either this one-to-many relationship or the one-to-one relationship. Okay, let's tackle the fun one, which is students and courses, which is a one-to-many relationship, or I'm so sorry, a many-to-many relationship. So this is where it gets tricky because I can have multiple students in a course and a course has multiple students. So where do I put my foreign key, right? And where do I put my ID? And the answer to this is something that's often called a join table. Because the answer is we need a whole nother table. And sorry, I don't want an index. I want a student ID column and a course ID column. And what this is going to look like, to go over here real quick, is an ID, the student ID column, and the course ID column. And it might look like this. A student might be enrolled in 2 different courses. Another student might be enrolled in both of those same courses, and another student might be enrolled in one course. Now, the situation I want to avoid, and this is where the unique constraint with multiple columns will come into play, is this. I don't want a student enrolled in the same course twice. You see what I'm saying? So let's build this out and then we'll add the unique constraint. And do you guys sort of see what I mean here by a join table, in that we have this student table, and let's put our lockers over here because we don't really care about the lockers. And we have this course table. Right, it has an ID and a name. And let's make all of these gray just so we can see more easily. And it was like Physics 101, Physics 101, and Computer Science 101. And we also need a professor ID. Right, because otherwise it might be confusing having the same names. And so this join table like has the list of students and what courses they're enrolled in. And so we can use these to connect these two things. So I just want to pause and see if folks have any questions there and if conceptually that sort of makes sense. Awesome. Because this is probably the most important thing. Carlos, yes, sir.
So kind of, I guess, taking a step back, the course to professor relationship was supposed to be one course can only have one professor, but one professor can do many courses, right?
That's correct. Yeah.
So how is it that we're able on the course list right there have two courses with the same name, but two different professors? Am I just reading that wrong?
No, you're reading that right. That one is simpler than it seems. We simply never set a unique constraint on course name. So there's just no rule saying that you can't have two courses with the same name. If I had done this, then that would be violated. But since the foreign key is about connecting to the professor ID, it has zero impact on the course name.
I think that's it. Thank you.
Yeah, good question. Um, this is an example of like maybe if we wanted to avoid not only the same course name, but the same professor, then we would use a unique constraint with those two values like this. Right? And that would make sense. And I think that's the scenario that you point out. Because indeed, we don't want that. Right? And we want maybe, so we can have Einstein teaching two courses, but also two courses with the same name. And in our data model, we're deciding that's okay, right? You could make a decision that, hey, I want every course name to be unique, and that's totally fine. That would just be a different design decision. But the thing we clearly don't want is we don't want the same professor teaching two different courses with the same name. Or, I mean, maybe we do. Maybe we're, a giant university. We're like University of Michigan, and maybe I'm teaching Intro to Computer Science in the morning, and I'm teaching Intro to Computer Science in the afternoon. That would just totally depend, again, on the real world domain that we're modeling and how we want to model it. So yeah, great question. Great point. So hopping back to students and courses, and in fact, let's grab our students and let's put them here, and let's grab our courses and let's put them here. And let's grab our join table and put it in the middle here. I'll kind of add a break so we can see. And we'll put this one over here, and I'll add a break so we can see. So again, we see here that the student ID and the course ID are how we can link these things up. I haven't like aligned the rows and the columns, but you could see how like with the join query, we could get all of this information. So let's go ahead and add this to our diagram. So the course ID goes here, and this is going to be, in fact, let me finish this and then let my brain catch up if we're dealing with one-to-one or one-to-many here. So this is one-to-many. A student can be enrolled in multiple courses. And this is also one-to-many, as in a course can have multiple students. So to build this out, our student course table would look like this. And the naming convention for a join table so that other programmers can easily identify it is the name of the two tables this joins together. And it's a good idea to give it a primary key ID. But its real job is to have a student ID, a course ID, and then a foreign key. And I think I can just write a foreign key like this, which is a bit shorter. So let's write them like this. I think this will do the job. Let's see if that complains, if I have that syntax right. Let me go ahead and run my code to make sure I don't have any syntax errors.
You have a typo with a null. So now 54.
Oh, yep, I totally do. Thank you very much. Let's run that again. Yep, that looks good. So now we can insert into student course student ID, course ID, values. And if I try to insert student and course IDs that don't exist, I'll get an error because Postgres is enforcing the foreign key references. And all the way down here, we see detail key not present in table student. So let's enroll a student in one course. Let's enroll that student in another course. And let's enroll another student in that course as well. So I've got a student in multiple courses and a course with multiple students. And just for fun, let's enroll our original student in the other course. And if I do select star from student course, we see here our join table. Now, we haven't talked too much about joins, but if I wanted to use this, I could do something like select star from student. Oh, excuse me. Tomorrow we'll dive deeper into querying, but just to give a preview. And for some reason, I just do not want to be able to type today. Join student course on student ID equals student course dot student ID. And I'm a bit surprised that I would have.
I think it was because when you did the previous line with the backslash, it threw it off.
Yeah, let's see. There we go. Yep. Thank you so much. So this is an example of that join table where I see we in fact see multiple rows for Alice because Alice is enrolled in multiple courses and Bob is enrolled in multiple courses. Or Bob is enrolled in one, excuse me. It looks like Alice is enrolled in a bunch. Andy, yes, sir.
I just got confused why you did the join if you already have the table that exists for it.
Right. Great question. So student course has a student ID and a course ID, but it doesn't have a student name. If we had an email here, it doesn't have a student email. It doesn't have all that other information, right? So if I want a list of all the email addresses enrolled in physics, I can get a list of all the student names enrolled in a specific course. Does that help answer your question? Because if I do select star from student underscore course, all that table has is the IDs. This table's only job is to be a linker. And if I say want to get names, I can actually do multiple joins. Let's say I want to do select student dot name course dot I didn't even give the courses. Did I give the courses names? I did. Good. Course dot name from student join student course on student dot ID equals student course dot ID. Join course on student course. Oh, and I've totally screwed up this query. Let me write it out here because I'm going to screw it up. Select student name, course name from student, join student course on student.id equals student course dot student ID. I can in fact do multiple joins. Join course on course ID equals student course ID. So if I have that query correct, I will get a list of all the names and students for the course. I'll get the course names and the students in the course where the ID is 2. And again, this is a bit more advanced. We're going to see this tomorrow. But remember that this join table here is a linker, right? Where I can use this in combination with the student table to find all the students enrolled in a course. And then if I link that to the course table, I can get the name of the course or the professor of the course because I get the professor ID. So this is a linker. Does that help answer your question, Andy?
Yeah, I think, yeah, I guess I was more confused because yesterday I think you said at some point that join creates a new table, but that's not the case, right?
Oh, I see what you're saying. That is not the case.
Okay.
What I had mentioned briefly, um, any SQL query sort of creates a new table. I'm not sure why I inserted. Oh, that's because I'm not sure why I inserted a professor so many times. Oh, it's because I've been doing these inserts over and over, and I didn't add a unique argument. So we have like 1,000 of the same professors. So under the hood, I don't think it actually every query sort of generates a temporary table, and that's the result that we view, including join queries. And I think I had mentioned that briefly yesterday, but not really gone into it.
Okay.
Yeah.
So you wouldn't be able to access it again unless you put in the command.
Say that again.
Essentially, it's not stored anywhere. It's just an instance that you get
Correct.
instance of the table. Okay,
Yeah,
makes sense.
you got it. Yeah. If you get fancier, there's way to store stuff. There's something called a view that's sort of like you can like give it a query and it sort of generates a table on the fly, but that's way out of scope. All right. So this is the big one. And I just want to see if folks have any questions around this many-to-many relationship now that we've seen the example in action.
Actually, yeah, I do have a follow-on question.
Yeah,
Is it important to have the student course link instead of just having a reference between student and course?
yeah, absolutely. Because if I have a reference between student and course, let's go ahead and delete this and delete this. And let's do it like that. And let's pull this over here. So if I do it like this, I could have one student enrolled in many courses. And let me pull this up here. Right, if I had like course ID, I could have a student enrolled. Well, it depends, because if I put course ID as a foreign key on the student table, well, I can have 3 students enrolled in the same course, but how do I enroll? Let me give a different name here. How do I enroll Bob
In
in
multiple
different
courses.
courses? Exactly. So with a foreign key, a plain old foreign key, there's no way for me to enroll Bob in multiple courses. And on the other hand, if over here for course I did a student ID, well, now I could have Bob in all the courses I want, but how do I have multiple students in a single course? So this is what you can't do with just the foreign key, is the many-to-many relationship, where I've got a bunch of students in a course and a student taking a bunch of courses. And so to do that, I need this join table because now, because a foreign key column can only hold one thing, right? So it's like I could only have one student enrolled in physics, and that's it. Or David could only be in one class. But with student course, each row represents an enrollment. So having a student in multiple courses is easy. I just have another row, right? And I can have the same student enrolled in multiple courses. I can have a course with multiple students. I just need to be careful not to enroll a student in the same thing twice. Does that help answer your question a bit?
I think so, yeah.
Yeah. I'd say this is the trickiest bit. I think using the spreadsheet can actually help a bit here. And again, if you just think about like, if we look at our student table over here, and I had a course ID, and I can only have one value in here. If this is my data model, it's impossible for Bob to be in more than one class at a time. Right? It's just not possible because this course ID can only hold a single value. So instead, I need a totally separate table to track enrollments where I can have Bob in a class here with one row, and then I can put Bob in another row. Yes, sir. Andy.
Yeah, you mentioned that there is a certain type that you would have to put in to be able to put in multiple values. Is that just out of scope, or am I wrong on that?
Oh, like a Postgres array type. Like what if we did something like this?
I think so, yeah.
Yeah, you could do that. You don't want to because it makes it impossible for Postgres to keep track of those relationships. right? With the foreign key, that's an excellent point because you could do this. Postgres does have an array data type. If we go to ChatGPT, Postgres array of ints column example. And let's give it a second and it'll do something. So it's easy to create, right? You just do this. The problem is insertion becomes trickier. If you want to start filtering, it becomes trickier, but it totally destroys Postgres's ability to handle relationships and foreign key relationships and maintain data integrity. Because a foreign key is a unique identifier of a row. So Postgres is not really set up to like take this and break it down into multiple foreign keys. It ends up it's not really built to do it, and we wouldn't want to build it that way because it ends up adding a lot of complications. Also, if you think about it, like in the real world, if we were using pieces of paper and graph paper to keep track of who's enrolled in a course, we probably would have a page that says enrollments that looks something like this, right? This represents real information because this represents a student's enrollment in a course and it represents a relationship between two different things. Because this is the more accurate way to model a many-to-many relationship. Yeah, great question. All right, we are just about at time. I know I ran a bit long today. Thank you all for being patient with me. Let me kind of go over our assignments for today, and then we will break. So the examples here are really good to look at. We have numerous ones. As I said, I also want to point out in the curriculum for today, there's also an example directory in which you can find our game store. And I don't think there's a lot of relationships here in the game store, but you can see a lot of examples of constraints, right? With regex, with check. In fact, we have added some positions. You could also do this with an enum, but you can check that a string is inside a certain value. So this example code is going to be a really good reference. And of course, I'll push up all the code I wrote as well. So the assignments continue on. The game store does build up a bit. We're giving you some pretty specific requirements for constraints and checks and quantity. And again, I think that example code will be a good guide, but you'll have to implement all of this in SQL. So this one is a bit more structured. And then the 32 flavors and 64 slices do build on yesterday's assignments, and today is a pairing day. So you'll want to work probably with a partner and maybe pick one of your codes to use. Or if you're coding in a group, this could be a great group exercise, and I think that's okay for pairing today. For 32 flavors, the new wrinkle is there are now multiple stores and employees can work in multiple stores. So stage one was there's only one store and we have inventory and we have employee data. But now you have to create a data model for multiple ice cream stores where employees can be working at more than one store. So that's going to challenge you on the many-to-many relationships front. And then for 64 slices, stage two is just continuing work here. When we get to queries tomorrow, there's going to be a lot more happening here with querying. So just continue building out the data schema, as I think this was a bit of a bigger task. And again, there's a lot of data in here, right? So your goal today is to create tables for all of this data. So it can all be in there. And there are a couple wrinkles in the data that will force you to figure out how you want to model things like, say, pizza toppings is going to be a little trickier. So those are the assignments for today. Let me go ahead and stop recording.